Hi everyone, so in this video we will be discussing resonance forms and the rules for resonance forms. So let's look at the acetate ion to begin to get into this concept of resonance. We have this ion. It has 2 carbons, the 3 hydrogens on this end. That's the boring end, right? But this end, this carbon over here, it has 2 oxygens. And when we draw this Lewis structure using all the valence electrons that we calculate, we end up getting a double bond for one of the oxygens and a single bond for the other oxygen. One of these has a double bond and 2 lone pairs. The other one has one single bond and 3 lone pairs, which again, that's one of those examples of the patterns of common formal charges in the previous table we just discussed. So if you have that handy, that definitely comes to be useful. And you see that it has that negative formal charge right here, -1. Now, when we look at this compound, should we label one of them oxygen number 1 or oxygen top oxygen, and that's the one that has a double bond, and the bottom one has a single bond with the formal charge, or the other way around? How do we distinguish between these two? And is one in a fixed place is what I'm trying to ask or pose. When we look at experimental data, the data shows that they're equivalent. So the CO bonds, the carbon-oxygen bonds, are equal in length. Now, if you remember, double bonds are shorter. There's more sharing of electrons. So naturally, this is a stronger force. So the atoms are going to be closer together. When you have a single bond, it's going to be weaker. So you end up having the atoms more far apart from each other. So how is it that you have a double bond carbon to oxygen and a single bond carbon to oxygen, but they're the same length? So what we actually see is that the length is 127 picometers, which is about halfway between it's about at the midpoint of a carbon oxygen single bond, which is 135, and a carbon oxygen double bond, which is 120. Remember, double bond stronger, so it's shorter. Single bond weaker, so it's longer. And you see 127 is somewhere in the middle for that. So what actually is occurring, even though what we have seen so far is we draw one structure once we figure out the number of valence electrons when we draw our Lewis structure, right? That whole process. We'll draw it one way. However, in a case like this, what we actually have is the possibility of resonance forms. And in reality, resonance is occurring. It's not like this acetate ion isn't heading towards this form, staying there, pausing for 5 seconds, and then moving to the other one. So even though this is how we describe it, or this is how we depict it on paper, right? Because we kind of have no choice. What actually ends up happening is that you have a hybrid of both. That's why when you look at experimental data, the bonds are the same, because you have this hybrid version of both where everything's kind of happening very fast, right? And it just turns into a mixture, a hybrid, right? So these 2 individual line bond structures are called resonance forms. So this is a resonance form. This is a resonance form. And I'm pointing at this one, set at the top, but we're supposed to be looking at this one because the other one has like these labels that we were asking about. But these are the 2 resonance forms. It's the same thing. And you can see that there's a double arrow between them, and this is indicating that these are resonance forms. So you can see that this oxygen that we're labeling just for visuals for you as part of this learning process. Remember, these oxygens are not experimentally different when you look at the bond length. Just for labeling, visualizing purposes, this oxygen at the top is first as a double bond, and then we show it as a single bond, and then the opposite for this one in the green. But remember, even though we're showing it as static forms, it's actually a hybrid in reality. Okay, so rule number 1 is actually discussing, or is related to what I was just yapping about in the previous slide, about how resonance forms are not how compounds actually are in real life. Remember, it's not like a picture where you can't snap a picture of a compound and you'll see one resonance form and then wait 5 seconds and snap another picture and see the other one. No, that's not how it is. So in reality, individual resonance forms are imaginary. So I know it's probably stressful to hear the word imaginary, because it feels like everything honestly in science always has conditions and it depends, and well, what about this? So this will be common. You'll see this in further classes if you take more science classes, that there's just always, it always depends, right? So for this concept, for resonance forms, the individual ones are imaginary, not because we can't draw them, but because in reality, the real structure is a hybrid, like I said several times. Compounds have unchanging structures. They're not switching back and forth between these resonance forms. So that's rule number 1. Always know that in reality, it's a mixture of whatever resonance forms you have. Rule number 2. Resonance forms differ only in the placement of their pi or non-bonding electrons. So pi are related to our pi bonds, meaning the bonds occurring between two p orbitals. Those have to do with double bonds or triple bonds. So every single bond is always a sigma bond. And when you have a double bond, one of them is a sigma, one of them is a pi bond. When you have a triple bond, one of them is a sigma, two of them are pi. And then we have non-bonding electrons, which are just our lone pairs. That's all they are. So neither the position nor the hybridization of any atom changes from one resonance form to another. So if the hybridization around this carbon is sp2, which it is, just because we have more than one resonance form, the hybridization actually stays the same if you look at it, right? It's still 3 electron groups, whether it's a double bond, single bond, whatever. There's 3 groups around it, meaning sp2. So all that's moving will always be electrons from double bonds or triple bonds, or non-bonding electrons, meaning lone pairs, right? So let's look at the acetate again. We have a red curved arrow showing that a lone pair from this oxygen is moving to this bond right here and to become a double bond essentially. At the same time, 2 electrons from this carbon oxygen double bond is becoming a lone pair. So it's kind of like this is pushing this bond out, because remember, carbon only wants 4 bonds around it. So if this lone pair were to come here and become a double bond, carbon would have 5 bonds around it, which not happy at all. And then here, now the other resonance form has the double bond up here, single bond down here. So what this image right here is showing you is how this second form comes to be. Now I have this great little GIF here, not created by me, created via Master Organic Chemistry. That's a website. It has a lot of great resources. I highly recommend it. Have it linked here. The link is on the slides. But it's showing in real time how this lone pair is becoming a pi bond. This pi bond from this double bond up here is turning into a lone pair. So that pi bond up there at the double bond is breaking. And here the pi bond is forming, meaning the double bond. And notice how the formal charge is it starts off at this single bonded oxygen with 3 lone pairs, and it ends up here because this is becoming the single bonded oxygen. So you can look at the GIF. I believe when you open the PowerPoint slides, you can actually pause it because I know it's going kind of fast. It's going faster than I'm explaining it, but like I said, great resource on this website. Here is another example. This is benzene. You will see benzene many times throughout this class. And it's this hexagon shape where alternating carbons have double bonds, right? Remember, anytime you have a double bond or you have some sort of lone pair, that can be delocalized, meaning it can be as a part, right? Remember the real compound is always a hybrid. So whenever you have double bonds, think about how that hybrid will have those electrons. I don't want to say moving around because that implies like one stage to the next stage to the next stage, but they're delocalized, right? They're not in one place. So you have these 2 possible resonance forms, and to show the electrons moving, again, we're having those arrows, and you can see that this double bond, right, the pi bond of that double bond can move over here. This one gets kicked, moves over here. This one gets kicked, moves over here. Remember, carbon only wants 4 bonds around it. So if you move one of these double bonds, but you keep this one up here, it's not going to be happy. So this is showing you here how these pi bonds are delocalized, where one carbon pi bond is broken and then formed, broken and then formed, and everything has a formal charge of 0 because carbon continues to have 4 bonds around it, no matter which resonance form you are looking at. Rule number 3. So in these previous examples, we have had some sort of symmetry, I would say, where the 2 or 3 resonance forms, I believe all the examples we looked at were just 2 resonance forms. So the acetate ion and that benzene, there was 2 resonance forms for each of those examples. And they were kind of equal. It was just that the electrons were, again, delocalized, not in one single place. But you can have different resonance forms, and this is rule number 3, where they are not equivalent. And when these 2 forms are non-equivalent, the actual structure, what it's going to look more like is the more stable resonance form. So you can have less stable and more stable resonance forms. How do you determine this? This is where it all ties together. Formal charges, right? That's the whole reason why we introduce these formal charges, is to be able to assign them to atoms to determine stability with regard to these resonance forms. So we will expect the true structure, for example, of the acetate ion to be more like that of the form that places a negative charge on the oxygen atom rather than the carbon. Oxygen, it's more electronegative, remember? It's higher on that electronegative trend of the periodic table. It likes electrons. It doesn't mind having electrons. It doesn't mind having that negative formal charge. Meanwhile, carbon, very unhappy. Does not like it. Very anti having formal charges. Carbon would rather have 4 bonds, whether it's a double bond and 2 single bonds, whatever combination you want to think of. It would just rather have 4 fully formed bonds. So here for this acetone compound, whenever you react it with a base, it turns into acetone anion. I'm not talking right. It turns into acetone anion, which is this right here, or this one, right? They're both logical representations based off the rules of drawing Lewis structures. However, one form has a negative charge on the carbon, which is possible because remember, if you have a double bond and if you have lone pairs, this is able to happen where the electrons are delocalized. Or you can have the negative formal charge on the oxygen, and this is much more preferred just based off of electronegativity of oxygen and how carbon is. It's very finicky. It just wants 4 bonds. So the actual structure, while remember it's not this picture and then this picture, this stage and this stage static, it's not static. It's a hybrid of these two. It's going to look more like this one because it's more stable. Okay, so rule number 4 is that resonance forms obey the normal rules of valency. And all that means is that carbon likes to have 8 electrons around it, meaning 4 bonds. Hydrogen likes to have 2 electrons around it, meaning 1 bond. And a lot of the other atoms are also the same. So oxygen wants its 8 electrons around it. Nitrogen wants its 8 electrons. Same thing with phosphorus and sulfur. And again, those are going to be the most common atoms you're going to see in this class. So for all those atoms I just named, you want 8 electrons around it. Carbon especially is it wants those 8 electrons. And hydrogen wants the 2 electrons. So any resonance form that you draw has to follow these rules. So here, for example, this is the acetate ion again. However, in the previous acetate ion resonance forms, which are the correct ones, right? This is an example of what not to do or what doesn't happen. We have this lone pair on this oxygen being formed into a double bond. Now, when this happens, but you don't kick that other pi bond on this bottom oxygen as a lone pair, when you don't do that, right, which is what happened here, you end up having carbon with 1 bond, 2, 3, 4, and 5 bonds, which gives it a negative formal charge, and it gives it a total of 10 electrons on this carbon. This is not acceptable for this carbon. It wants 8 electrons around itself, 4 bonds. So 8 electrons is also 4 bonds. So this is not a valid resonance form because it's not following the normal rules of valency. And then rule number 5, last one. The resonance hybrid is more stable than any individual resonance form. So that's the whole reason we're learning about this, because resonance gives stability to compounds. The larger number of resonance forms a compound has, the more stable it is, because these electrons are delocalized, aka spread out over a larger part of the molecule, and this increases the stability. So keep these resonance rules handy, keep them nearby. They will definitely be useful for you to look at when you're completing problems related to resonance. So here we have a useful technique for drawing resonance forms. And all this is again, a pattern. Remember, organic chemistry is about patterns and being able to apply them. So this is the most important pattern for drawing resonance forms. So in any 3-atom grouping where you have a p orbital on each atom, so let's say, for example, a carbon, an oxygen, an oxygen. A carbon, an oxygen, an oxygen, right? Carbon as the Y and then oxygens as the X and Z. You have a double bond here between this X and Y and a single bond to the other Z, aka the other oxygen, and you have a lone pair, for example. It could be any of those, but you have access to p orbitals because it happens to be in oxygen, whether it has those lone pairs or not, whether it has that lone pair or not, or a radical. Now, you have this as one resonance form, and what happens is, remember, you always move the double bond, or this lone pair over here is what I was trying to say. I was thinking of this one. This lone pair moves to be a double bond, which you can see here, which ends up kicking this double bond to be a lone pair, which is what you end up having over here. So this is a very common pattern, very important for you to pick up as you practice. And here this is showing you that atoms X, Y, and Z could be carbon, nitrogen, oxygen, phosphorus, sulfur. So far what we have seen, a good example of this is the carbon and the oxygen version of this in acetate. But it could be any atoms with p orbital access, but most likely it's going to be these, to be honest. The asterisk means that a p orbital is vacant. It either contains a single electron or a lone pair. So let's look at this example, and I'm going to use the highlighter here. How many resonance structures does the resultant anion have? Now first, what does that mean? So you have this compound 2,4-pentadione, and it's reacting with the base, and you end up getting an ion as a result. So that's what that means. So that's what we're looking at here. Now, notice that there is this little squiggly line. All that means is that we are kind of cutting it right there and just focusing on this part of the compound. Right there. So just for clarity's sake, that's what we're looking at right here in this center area. Is we are looking at that part of the compound that I circled. Okay, so we got that out of the way. We have two, portions of resonance forms here. We see that we have this oxygen, back to my laser point, we have this oxygen with two lone pairs. We have a carbon with a double bond, and you have this carbon with a lone pair on top of it. Carbon, this lone pair on top of this carbon, right? And this carbon has a negative formal charge. It doesn't like that, remember. What it's going to do is that will be delocalized to form into a double bond. Remember, carbon only wants those 4 bonds, so it's going to have to kick one of those, that pi bond from that double bond up here into a lone pair. So here you have that double bond we talked about and a lone pair up here on this oxygen. So this right here, what is being shown in the center panel, in the middle panel, is what is happening right here on this first compound. And then you end up getting this resonance, or when we draw it, right, we're depicting it. We're depicting this resonance form, which can also change, right? Because we have, remember, the XYZ pattern where you have 3 atoms in a row that have access to p orbitals, aka a carbon, an oxygen, nitrogen, 2 carbons, an oxygen, for whatever the example is. So here you have CCO, and it's the single bond, double bond. So when you have that pattern, this is what's going to happen. A double bond moving here, kicking this double bond over here, this double bond being kicked off into a lone pair, and you end up getting this resonance form. So you have a total of 3 resonance forms here. And they're not exactly, I would say, completely equivalent. The 2 equivalent ones you have are these 2, the center and the right hand. And then you have this less equivalent. It's different from the other 2.